Next up, we have Derek Carroll from Repligen.
Hello, everyone. In this presentation, I'll introduce a new product that we've been developing at Repligen that automates the UFDF process using inline concentration measurements. So we'll review some of the market needs and challenges that the system is meant to address. We'll also highlight components of the system that need to be integrated to develop the solution. And I'll give a technical overview of how it works and some of the data we've generated during the development. So in April of this year, there was a biotherapeutic survey of developers and contract manufacturing organizations, and they showed the top two areas of interest for new product development were real-time inline product sampling, as well as new automation instrumentation. And these two areas are the core of this product, and so unifying our inline analytics solutions as well as our automation instruments, in this case Repligen's lab-scale TFF system, is how we plan to address these needs. So for TFF, the challenges that we see are dependence on mass balance, fragmented processes which require offline concentration measurements. They have disjointed data locations that need to be unified after the experiment. Variability from run to run, and then also a risk of error from cumbersome offline analytics requiring dilutions, determining accurate holdup volumes, as well as making sure that tearing of scales is accurate when used during mass balance. So to address these challenges, we've unified CTech's FlowVPX system, which uses variable path link technology for inline spectroscopy, and as well as the KrosFlo KR2i TFF System. So by unifying these two systems, this allows for automated process control, yielding highly accurate concentration results. So the FlowVPX can rapidly acquire data at multiple path lengths with a concentration measurement based on 5 path lengths that is measured every 5 seconds. This range of path lengths will actually allow for concentration measurement of samples as low as 0.1 mg per mil all the way up to 300 mg per mil without any need for sample dilution. So the core technology behind this capability is the ability to vary the path length. So to get an accurate measurement according to Beer-Lampert's law, absorbance is equal to the product of extinction coefficient, path length, and concentration. And you need to be in the linear range for your spectrophotometer to get an accurate reading. So in traditional uv-vis spectroscopy, the path length is at a fixed value, which is based on the geometry of the cuvette that sample is prepared in. And the concentration is what is varied by diluting the sample. So therefore, before you even take a measurement, you're already affecting and adding variability to your process or to your measurement. However, with variable path length spectroscopy, the path length becomes a variable. So you're actually able to now change the path length, and the need for dilution goes away. So without dilution, this technology can actually be put in line, and these absorbance measurements can be taken at those various path lengths continuously. This allows for robust processing and continuous monitoring throughout the entire process. Now a bit about the KR2i TFF automation system. So this is a bench scale TFF system that allows for 13 automated process control modes, has robust processing across a range of starting volumes, minimizes risk with configurable flow paths, and is flexible to various configurations in terms of accessories as well as filtration technologies. So by introducing the FlowVPX into a TFF flow path, you now have a very powerful tool for running your UFDF process. So in the setup shown here, you can see the FlowVPX is placed on the feed line where it's most representative of the concentration inside the recirculation vessel. And with this placement, accurate measurement can be taken throughout the process, so you know the concentration at any point. So combined, these two technologies are being released as the KrosFlo KR2i RPM, with the RPM standing for Real-Time Process Management. This integration has been enabled by a newly developed software platform, and with this software, TFF automation control can now be based on inline concentration. It provides real-time overviews of every step and combines all data set locations to a single output. So now to get into some of the results generated by this system, I'll show you an example of the types of trials we've been doing during development to prove the system's performance. So in this example, we've set up with a CDC concentration diafiltration concentration experiment. The initial target was 38.5 for protein concentration at diafiltration stage with 4 diavolumes, and then a final concentration target at 150 mg per ml. So show a time-lapse video of this in progress. So in this video, you can see we have a constant feed setup. Vacuum's drawing an additional feedstock. As it's concentrating, that volume is being maintained. And the concentration continues to rise through the initial concentration. And you can actually see in the data there's an inflection point where the feed vessel is, additional feed vessel is drained, and the process continues until that initial concentration's been reached. Next, in the diafiltration stage, the concentration is of course maintained. There's a diafiltration pump that is adding additional buffer into the line that maintains constant volume, and we can see that that concentration is held steady, and the FlowVPX measures that as the number of diavolumes is reached. So lastly, final concentration. So this takes place, the system continues to concentrate, the recirculation volume lowers as it gets down into the final stage, and we can see that it measures accurately all the way up to that target of 150 mg per ml. So next, we wanted to get a comparison of how these new capabilities compare between using a more traditional method with a mass balance experiment. So we set up a process with a concentration factor, diavolume, and final concentration factor, and then compared that to a very similar run to what I just showed, but also looking at the conductivity also being measured in line during the diafiltration stage. So we had a target for what that conductivity would be after we performed that buffer exchange, and made that the set point as well for inline analytics throughout the entire process. All right, so the results show a much more efficient process when using inline analytics. In this data, we can see that the concentration targets are all met within a few percentage points. And the diafiltration actually ended as soon as that conductivity of the buffer exchange was complete. So if you compare that to the mass balance, you can see there was some overshoot in the concentration targets. There was additional time spent in diafiltration mode beyond what was needed to achieve the exchange that we wanted. We also see those kinds of sensitivities that I mentioned requiring very accurate scale measurement, especially as those volumes get very low, accurate tearing, hold-up volume calculation. All of those things introduce error that are present within the traditional scale-based TFF runs. So in this run, we also wanted to ensure that our concentration measurements were consistent across spectroscopy platforms. So we took offline measurements with the Solo VPE, which is also a variable path length technology, as well with a fixed path length cuvette for offline dilution. And we saw good consistency in the measurement across all the different platforms. Okay, so thanks for your time and learning about this new system. We're confident that the you'll see the same types of results if you start to utilize this technology in your own processes. And yeah, please come by our booth if you want to ask any questions, and have a few minutes if we want to take some right now. Yeah, and so it is flexible, and this is a specific application that we really went after first. We saw a lot of potential here, but really it's a flexible technology. We can look across a full range of the uv-vis spectrum, use a variety of different path lengths, run simultaneous measurements at multiple path lengths throughout the process. So there's a lot of additional applications that we could start to think about this for. Mm-hmm. Okay, yeah, come by booth 801 if you have any additional questions, and thanks for your time.